Oh, see, that was the first where I was like, what is going on? Yes.
All right, guys, page 18 in your packet. We have a couple of more identities to go through. These are double angle identities. So anything inside the angle, if it's showing 2 theta, it just makes it harder to work with. So if we can kind of split that double angle inside that trig into just in terms of theta, then we have a much easier time kind of moving, combining things around. So anytime we see a double angle, we want to try to break it down into its theta parts instead of that 2 theta inside the parentheses. Remember, anything inside the trig function, it's always hard to work with it, right? We need special rules to deal with it. It's not as easy as just distributing and splitting up. So these are the rules here. So the first is sine of 2 theta. Sine of 2 theta can be broken down into theta of measures. So it's just 2 sine of theta times cosine of theta. And that allows us to, they're equivalent. So that, if we do this in terms of 2 sine theta, cosine theta, it's easier to work in values and find what we're trying to do. Cosine of 2 theta, there are 3 variations: cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus 2 sine squared. But the reason why there's 3 versions is because we can use trig identities to replace the cosine squared or sine squared in terms of the other trig function, right? So if I gave you cosine squared minus sine squared, you'll be able to convert that to be in terms of cosine by replacing sine squared with 1 minus cosine squared, right? You guys got pretty good with that on the quiz, and you guys were able to seamlessly, pull, take a trig function and find the replacement for it in terms of the other trig function. So that's what these 2 are doing. It's just, if you know cosine squared minus sine squared, you can get one in terms of the other using the Pythagorean identity, and these are the other 2 variations. Sometimes we want one variation versus the other. It just makes things where we're able to get to our solution a lot faster. Tangent of 2 theta looks a little more complicated, but tangent 2 theta, we can break it down into 2 tan theta divided by 1 minus tangent squared theta. Okay. Basically, this is the way that we can get rid of that 2 inside that trig function. Yes. Yeah, so I think we're talking about where you'll get to use a formula sheet, but if you decide not to use a formula sheet, there's going to be a bonus point associated with it. So if you decide to not use it, you can earn that 5. I think it's either like 3 to 5 points bonus. But so I think that's what me and Ms. Latimer are talking about right now. But looks like at the very least you will get to use the formula sheet, but there may be an incentive for you to memorize the formulas. Okay. So number 1 here, use double angle identities to find the exact value. Okay, so 2 sine 15, cosine 15. Now, we know that 15 degrees is not a unit circle value, but what if we can push this back in terms of a double angle, right? Because right now, this kind of looks like this form, right? So if my theta is 15, and if I know that I have this matching part here, I can turn this 2 sine theta cosine theta back into sine of 2 theta. So if I have all the matching parts here, what is this equivalent to? Sine of 2 times 15, right? Because I'm just taking that 15, using the double angle identity, and just working backwards, right? And the reason why we're doing that is because, well, 15 is kind of hard to work with, but if I can get that 15 to double, then 2 times 15 is 30. sine of 30 is a unit circle value, which is 1/2. Yeah. Okay, so today we're just going to be working with these double angle identities. So we're going to expand them. And just like how we've done in the past, we're going to work on one side and find our way to the other side. Okay, so number one here, use double angle identities to verify the following identities. Cosecant of 2x. Now, we don't have a double angle identity for cosecant, but we do have a double angle identity for what? Or sine. So what's equivalent to cosecant of 2x? Yeah, 1 over sine of 2x, right? These are the same, right? And now I can expand that double angle in the denominator. See if that will help me reach where I want to go. So I can expand that double angle identity. We know sine of 2x can be broken down into 2 sine of x cosine of x. Okay. Look at what we have. Look at where we want to go to. Are we closer to our result? Okay. So the nice thing about multiplication and division, we can just quickly separate them into individual fractions to help us see things better, right? Because 1 over 2 sine x cosine x, isn't that the same thing as 1/2 times 1 over sine of x times 1 over cosine of x? Maybe that will help us see things a little better, right? What's 1 over sine of x? Same thing as. All right, so we have that portion. What's 1 over cosine? So we have all the pieces here, right? We're just kind of seeing the different parts a little bit clearer here. There we go. We have our right side. We verified it. That's it.
Explain the last step.
Yeah. So are you good with breaking this fraction into 3 different sort of parts? Okay. So now let's look at each individual part. 1/2 is just 1/2. What's the same as 1 over sine of x? Cosine of x. That's, and then 1 over cosine of x, same thing as secant of x, right? So my order is different, but you can, I mean, I'll give you full credit here. It's the same thing. Yeah, you can rearrange anything with multiplication or addition. Okay, number 2, cosine of a minus sine of a. I want to get to the right side, cosine of 2a. Okay, I'll show you how to do this from both sides, and then you can, it may be easier going at it from the right side, but let me show you how to get to it from the left side. And then, you know, on the test, you always get to choose. You can always choose whether to go from left to right or right to left. Sometimes you can go from both sides. Usually I would go from left to right, but in this case, looks like both ways can work. So if I want to get from cosine of a minus sine a to something involving cosine of 2a, let's look at what we want to get to. We want to get our square to show up, right? Because if I can get my squares to show up, then I have a much better chance of converting it into something that is cosine of 2a. So what can I do to quickly get a cosine squared and sine squared to show up? I can multiply that by what? Yeah, I can multiply by the conjugate, right? The conjugate is a quick way of getting things to change. But if I want to do the conjugate to the numerator, I also need to do what? Conjugate to the denominator, right? So conjugate is cosine of a plus sine of a. All right, so anything I do to one side, I need to do to the other side. So really, it's really over 1. Let's FOIL the numerator out to see what we get. If I FOIL that out, I get cosine squared a plus cosine a sine a minus cosine A sine A, and then minus sine squared A. Sorry, I ran out of room. What's convenient about the middle terms? Okay, cancel out. So I'm left with cosine squared minus sine squared. And what can I do with cosine squared minus sine squared? Good. Cosine squared A minus sine squared. I can reach my goal here because that's what my identity is. Let me show you how we can get from the right side to the left side. I just want to give you, as many tools as possible. So cosine 2A, looks like I want to try to work in cosine and sine. So I'm going to choose the top one here, cosine squared minus sine squared. Remember, I cannot cancel across addition or subtraction, but there's something I can do with this numerator. What can I do with this? Factor using what? Difference of squares, right? So if I do that, right, a squared minus b squared is a minus b times a plus b. I bet this is all a here. Anything match and cancel out? Cosine A plus sine A, and that ends up with my left side. Okay, just want to kind of give you a different look for how we can. So it's basically we're working two example problems just to kind of see different ways of getting from one side to the other. But obviously on the test, you can always choose which way to starting. You never have to do verification from both sides. Okay. All right. Any questions? All right, number 3. Let's start on the left side. What's something that we can do based off of what you see? You start off by doing what? Yes, what's a better way of saying it? I don't want us to make a mistake there. Can we just say sine squared plus cosine squared? Oil, right? Anything you have parentheses with squared outside, always write it out twice because there's more to it than just sine squared and cosine squared. There's gonna be a middle term that we got to worry about. So the safest thing to do is to write it out twice so that you can kind of remind yourself to distribute and you don't forget about there's going to be more than just sine squared and cosine squared. So I'm going to follow this out. I'm sorry, I didn't mean to put that right side here because we're only working on one side. All right, anything come together here? Yep, that becomes 1. Oh, sorry, there's a -1 here, right? So that's also part of what I need to clean up. Okay, so I forgot to include that -1 there. Okay, so that's 1, right? So 1 minus 1 is just 0. So we know all that goes away, right? And the two middle terms combines to be what? And is that an identity? Yes, right, so 2 sine x cosine x can be put together to make sine of 2x. Yeah, we took care of the +1 and -1 with that sine squared plus cosine squared. Yeah. Yeah, I'm skipping a few steps there, but let me know if you want me to connect the dots or if you want me to go back over what we did. Number 4. This one, I do think starting on the right side may be better because it's just easier to get from a complex down to a simple rather than a simple to a complex. To go from a simple to a complex, you got to introduce something into the problem to make it bigger, and that's usually a little bit harder. So let's talk about let's start on the right side and move to the left. Now, what's something that you want to start with? I would leave this here. I think sometimes that cosine x plus 1 is there to help you see things down the road. It's not wrong, but typically I don't want to distribute unless I see clearly a reason to do it. And sometimes having that separation helps us match parts a little bit better. Yeah, that cosine 2x, right? Maybe we can look to expand that out, right? Get it into a form that's easier to work with. Now, there's 3 variations, and it's more along the lines of, making an educated guess. Based off of the problem that you see, which one do you think could be a good fit to start with? And why would you pick?
2 cosine, like,
Why would you go with that one?
Is it the n on cosine?
Yeah, because everything is in terms of cosine, right? So our educated guess is, well, if I get everything in terms of cosine, then it'll be naturally easier to merge things together if I have everything, the same trig function. So I'm going to replace that cosine 2x with 2 cosine squared x minus 1. And I'm leaving my denominator in factored form until I see a good reason to distribute through. Right, because the cosine 2x gets replaced with 2 cosine squared x minus 1, and there's another minus 1 there. So I highlighted to show what I'm changing, and everything else is staying the same. All right. So now I'm moving forward here. Everything's I got that double angle to disappear. Everything is going to be easier to work with. What would you do next? Anything in the numerator that we can do?
We combine like terms, right?
Combine like terms, yep. 2 cosine squared x minus 2.
Divide the twos.
Yes,
You are going to do something with the 2's, but we can't do this. We can't cancel out because this is connected to that minus. But what can we do in the numerator? Factor. There we go. GCF. I feel like on the you guys did really well on the quiz, but I did notice that sometimes your steps are not as efficient as it could be, which is fine. It's just that it's taking longer for some of you guys to get to your answer. And I think a lot of it can be solved if you look for GCF. So for instance, I saw, like on the quiz, it was like, I'm just making something up. Let's see. Some of you guys were trying to get everything through sine and cosine, which is fine. You still got to the answer, but sometimes if you can factor the GCF out to begin with, it kind of moves the problem a little faster. That's just a suggestion, yeah.
Wouldn't it be easier to just distribute a new denominator and just divide it straight down and get to your answer?
That's the problem, though. If I distribute that through, I get 2 cosine x plus 2. I still can't cancel the 2's, right? So I get 2 cosine of x plus 2 if I.
So you can't, like, what about like the -2 and the +2? You can't like 5 plus 2.
This -2 and.
And it wouldn't be a +2 if you distributed it.
It would be, but if I have this. So you want to do this?
Yeah, like
I
divide.
can't.
Oh.
That, remember, anything attached to plus or minus, as tempting as it is, if we do this, we're changing the problem. Now, if it was this, if it was just that, and no attachment to addition or subtraction, yes, this here can you start canceling out. But anything you have plus or minus inside your expression, they're kind of stuck. And if you cancel out, you're changing the value, and you're not making an equivalent problem. So GCF comes out. So if I take out a GCF of 2, that means I'm dividing by 2. So 2 divided by 2 is 1. So all right, I'm getting a little closer, but I still can't do this, right? I cannot cancel this out. But there's something that we can do with the numerator still. The difference of squares, right? A squared minus b squared is a minus b times a plus b. Am I able to reach my goal?
Like for that one, if they were both +2, would you be able to cancel?
I know this is kind of frustrating, right? Because it's like, why does that not work? Right? So let me give you a example here. What's 1 plus 3 over 4 plus 3? 4 over 7. Okay. Let's say I could cancel out. Is that the same thing as what we know to be true? It's not, right? So that's why we can't do that. But if it was like, 1 times 3 times 2 times 3, right? This is 3 over 6. But if I were to cancel this out, I can do that. I will get 1/2, and I'm still getting something equivalent. So hopefully that convinces you that you can cancel the cross multiplication, but you can't cancel the cross addition, because you're not going to get the same thing as what you started with. All right, page 19. Okay, number 5. All right, secant of 2x. We don't have a double angle identity for secant, but we do have double angle identity for what? Oh, sorry. Yeah, I think that's better, right? Let's start on the right side, move to the left. It's a lot easier, a lot faster. Okay, so let's start on the right side here. Cosine squared plus sine squared is. Yeah. Cosine squared minus sine squared is the same thing as cosine 2x. And the 1 over cosine 2x is the same thing as secant of 2x. Okay, yeah, much better, much faster. Okay. Do we have a triple angle identity that we learned yet? No. So we're gonna have to find a way using something that is available to us. We don't have sine of 3x, but what if we can split that into something that we can work with? So we have to rely on sum and difference identity, right? 3x we can break down into what? The 3x. What if I split 3x into 2 different parts? So what could I use? What adds to 3? 1 and 2. So can I get it down to x plus 2x? Doesn't matter whether you do 2x plus x or x plus 2x. We just follow the rule now. Remember, we can't distribute the sign through, but if we can, anything inside the parentheses, we have to deal with a special rule here. So treat x like A, we'll treat 2x like B, and we'll expand them out so that we can get each of them a little bit easier to work with. Okay, so I can do sine x cosine of 2x plus cosine of x sine 2x. Everybody good so far? Where did I get that cosine from? The cosine came from, this is the sum and difference identity that we learned last time. So we're just using the formula here, right? Okay, so at least we've gotten it down to double angle that we have identities for. That's good. But look at our goal here. Our goal is in terms of sine. Okay, we can't do anything about the sine 2x, right? There's only one variation of this, so we're kind of stuck with using that one. But cosine of 2x, which one would you choose? Based off an educated guess, you would use what? Yeah, 1 minus 2 sine squared, right? Because everything's in terms of sine, so the more that we can move in terms of sine, the faster we can probably move through our process. Okay, so I'll replace the cosine 2x with 1 minus 2 sine squared x. Okay, I'm going to distribute that sine through. I'll do that later. This one I have no choice. There's only one identity, so I can't get just sign to show up, but we'll see what we can do with that. Okay, distributes the sign through. Now here, we don't distribute through. There's no plus or minus, so we can just merge cosine with cosine and make it cosine squared. Okay, look at where we are and look at where we want to be. We're getting closer, right? We do see that sine cube, but there's still something that we can play with. Yeah, there's something here that we can replace. You see an identity? You see an identity that we can apply?
5 is cosine squared.
Yeah, that cosine squared, I can replace with what?
Sine squared.
Or
I mean, yeah.
1 minus sine squared. Okay. So we're just kind of little by little kind of piecing things together. Getting our working towards our goal. Okay, I'll distribute the 2 sine x through, and hopefully after I combine all the like terms, I'm able to. Okay, like term, like terms there. Okay, number 7. Okay, is everybody okay with 6? Same idea, right? Cosine 3x, I can break it down into what? Yeah, cosine x plus 2x, but I have a different rule for that. Okay, I'll treat x like my a, I'll treat 2x as my b. Remember, the plus is going to be with the minus. And the rule is going to be written like this, so you got to be able to know how to read it, right? If I choose cosine plus a plus b, then I got to match the top operation with the top operation, right? All right, what can we play with here? We can play with these two. This says we have no choice. There's only one way to expand this, but cosine 2x, based off of where you want to go, which one would move us faster towards our goal? Yeah, let's just get, we want everything in terms of cosine, so let's just, I mean, it wouldn't be wrong if you chose another one, but it will just take a little bit longer because eventually you got to convert that sine square back to cosine square. So I can kind of see that and make my way towards my goal a little faster there. It feels like the same process, right? But it's good that we can get that practice in. All right, we want everything in terms of cosine. So what's one last piece that we can change? I would just say just the sine squared, right? Because I'm gonna put the 2 cosine in front. It just means that it just feels weird having that parentheses on where you got distribute from both sides. So if I just have those 2 terms together, feels a little bit cleaner. Just distribute once. Okay, like terms. 4 cosine cubed x minus 3 cosine x. There we go. Okay, let's start on the left side for number 8. We do have an identity for tan 2 theta, but let's work towards that identity instead of expanding out. It's hard to get to cotangent and tangent here. So look at your trig identity for tangent. What do you notice about the identity for tangent? It's all in terms of what? All in terms of tangent. Okay, so we can do that, right? We can get that left side in terms of tangent and merge things a little bit cleaner. So what piece can I change? Huh? Or cotangent becomes. Now, okay, here's the thing. Can I move this cotangent up to this numerator? Yeah, that minus sign is stuck. Now what I can do is I can create a fraction within this space. Right, feels nicer if I can do that, but I got to go through complex fraction here. It's just that minus sign is preventing us from moving that cotangent too far away. So again, cotangent can be written as what? In terms of tangent, 1 over tangent, right? Okay, guess what we need to do there? Yeah, we got to try to find a way to merge those two because that's a little messy down there. Right, so I need to find a common denominator within that space below. Okay, what's my common denominator? Tangent, okay. Any balancing needed for my first fraction? Nope, that 1 can be copied down. Any adjustment here? Yep, I need that tangent up in the numerator as well. So tangent will be tangent squared. Still got that 2 sitting there, but see 2 over. Okay, I still have a complex fraction, but at least I got that denominator to be pushed together. What can I get to? What can I do to get this out of complex fraction here? Good. Dividing by this fraction, the same thing as multiplying by its reciprocal, right? So 2 times. Flip that, move that to the top. Am I close to matching with where I want to be? Yeah, this is the identity, right? The identity is 2 tangent theta over 1 minus tangent squared theta. That's perfect. So there we go.
But isn't it back in like these like half angle identities, so we can sort of.
Yeah, no half angle identities on this test.
Probably like next year.
Mhm.
It's not as intense.
No half angle identities, no half angle here. All right, guys, encourage you guys to start reviewing. I have the test review. I got a key, so if you want to work through that, that's good. But don't forget your phones. We'll have tomorrow to review.
These last two ones, yes. Yes. Just get rid of, oh, do you just get rid of?
Because 2 tangent,
What?
tangent 2 theta is equal to 2 tangent theta is 1.
You just rewrite that and then. Oh.
But if I can reach to this side, then I can make my conclusions.
No, I usually. Then this would be. Yeah, so 2. Or.
See that 2 tangents?
Yeah.
It's part of that rule, so you have everything that you need. So that's just tangent 2 theta.
Oh,
Yeah.
okay,
Perfect.
that is just that.
There you go.
Okay, and then for this one, how did you get through the 2 sine x squared to what it was?
So I just made the 2 cosine come together. It'll be easier later. I replace that sine square as 1 minus cosine theta.
Okay.
And I just distribute the cosine, 2 cosine theta. Oh, wait, it's 2 sine squared
Yeah.
cosine squared. Oh, I merged those 2 together.
Right.
Made it sine squared.
Squared.
But then,
There's a minus there somewhere. And then maybe I wrote it out.
so you see that sine,
Oh, these are, well, this is one term, right?
yeah, it's all one term.
Okay, so this extra
So-
sign is just not needed.
Right.
That's what it is. Got it. Thank you.
So Mr. Yang, when, like, how do you know when to do,
You see, that's where I put my phone in the spot.
when you do